Okay.
Hello, I'm Jessie, and this is George and Tony, and we are presenting on the vapor-liquid equilibrium plot. Under ambient conditions, most vapors are considered ideal. The purpose of our experiment was to figure out if our methanol water equilibrium system fit this model at normal pressures. If not, what does? First, we're going to go over the topics for discussion. I'm going to present on introduction, theory, and the apparatus. And then Tony and George are going to present on procedure, results, the conclusion, recommendations, and the references. First, introduction. Our objective was to determine the vapor-liquid equilibrium conditions of a methanol water system. This was achieved by creating various concentrations of methanol, distilling those concentrations, sampling the liquid and condensed vapors, testing the samples on a refractometer to find out the refractive index values, and finally plotting the collected refractive indices against a standardization curve generated during the experiment. And all of that will be covered more in depth during the procedure sections. Okay, so for the theory section, solutions in equilibrium behave differently due to the interactions between their components. And that's why different equations exist to take into consideration those differences. If no molecular interactions are taken into account, then the equation assumes ideal conditions. And that's what Raoults' law is, as seen here. However, this obviously doesn't work for real life situations. And so we need to add in the corrective factor, which is gamma. And many different models exist in order to solve for gamma. We explore those models with our equations sections. Van Laar fits the activity coefficients given the parameters. And then we have SRK, which takes into account the characteristics of each of the components and the conditions of the experiment. And they determine the Z value for the vapor and liquid. From this, K is calculated. As you can see here is our apparatus. We added in the methanol and water mixtures into the funnel to the left. And obviously went down to the pot here at the bottom. The heating mantle heated the liquid and turned it into a vapor, which went up the column and down the condensing tube. And over here we have the liquid extraction tube, which is where we hooked up our syringe to remove our liquid sample. The vapor sample was just collected coming out of the condensing tube. And here we have our refractometer.
All right, so the first thing we had to do was to be able to charge the actual pot on the bottom of the distillation column. So we have the initial moles of methanol. We set it to 3.5 moles because we have that degree of freedom. And the equation to solve for the moles of water then is the mole fraction of methanol is equal to the moles of methanol over the total moles. We knew we wanted to first initially charge it with 90% methanol and 10% water. So doing this calculation, we know the mole fraction and the moles of methanol. We can solve for the moles of water. Moles of water we can't directly measure out, so we had to convert that to volume, which is the following equation. Volume is going to be equal to the moles times the molecular weight divided by the density. Okay, for part B, to be able, once we have those samples, we're going to take refractive index, and from there we have to figure out the mole fraction. to be able to do this, we have to create a standardization curve. And part B is going to tell us what volumes of water methanol we have to add together to get a 10 milliliter solution of a specific composition. So our total volume is equal to the volume of the methanol plus the volume of the water. The problem is this is one equation, but we have two unknowns. We don't know the moles of water and we don't know the moles of methanol. But we do know the composition. We know we want 90%, 80%. We do it from 0 to 100. So we can set the moles of water equal to, in regards to the moles of methanol and the composition. Finally, you plug that into the final volume equation and we'll get the modified total volume equation. From here, we know everything except for the moles of methanol. So we were able to put it into solver and find the moles of methanol for a specific 90-80% mole solution. Okay, so for part A, we were initially charging it, when we used our pre-lab calculations, we found we'd initially charging it 141.4 milliliters of methanol and 7 milliliters of water. This gave us our 90% methanol solution. From here, the distillation column, we put in the temperature probe, we started the cooling liquid, and we and we started the heating mantle. The heating mantle was set first to 10 to allow the heat to heat the pot up much quicker, and then once the pot reached boiling, we brought it down to 7 to continue that boiling. After 20 minutes, the solution was allowed to equilibrate while it was boiling, and we took a sample, a vapor sample, and a liquid sample. Again, we took the liquid sample with a syringe out of the bottom of the pot, and we took a vapor sample from the condensate coming out of the condensing tube. We took these at the same time, and that's important. Also, what's important is to not take too much sample, because you can mess with the total volume of the pot. So when you dilute the sample, you could dilute it maybe too much and not hit your target mole percent that you're looking for. And then this was, like I said, diluted to 80%. It was ran for 20 minutes to equilibrate and just continued. And then these samples were taken to the refractometer, which I'm going to show you how to use the refractometer. So the refractometer, the top prism has to be taken unhinged, and you wipe it off with a chem wipe to make sure that there's no nothing left on there. From there, you use a pipette to drop a sample on the lower lens. From the lower lens, you quickly close the top prism. This was important because we weren't using any cooling liquid, so you wanted to close it quickly to ensure there was no evaporation of any of your sample. Then you close the top prism and you bring the light source up to the top. You look through the scope and you'll see something similar to the picture below. You use the dials to actually get the picture below. You have to have half of it be the darker area and half be the lighter area. This, from here, you digitally hit the read button and it will give you the refractive index level. Right, and then the procedure for part B was actually making our standardization plot. We had all those 90%, 80% of the 10 milliliter solutions, and these were tested on the refractive index, or for the refractive index. The refractive index was then plotted versus the mole percent of methanol. So here's our standardization plot. You can see the general curve. So what we did to be able to read a specific mole percent of methanol for any given refractive index, we actually fit a curve to it. And from here, we were able to then use Excel to solve for any refractive index that we were able to put in. What's really important, this standardization curve is very, very important because it's kind of the basis for the other procedure of our lab. If we don't have a good standardization curve, we won't know necessarily what we won't be able to read the compositions very accurately. So we found some literature values for our standardization curve, and you can see that our lab data and our literature values are very closely fitted to each other. So here's our actual data. What happens is every time you took a sample, we took the temperature, and we also knew the pressure was ambient pressure. And using that equation from the standardization curve, we knew that our liquid sample refractive indices, we knew that straight down, and we were able to use that to find our liquid sample mole percent. The blue dot area are outliers that were significantly deviated from it, and that we had to drop out for a better data fit for later what Tony's going to talk about. So now I'm going to let Tony go to the rest.
As you can see from the data up there, the approximate liquid concentration in the very far left column should be ideally approximately close to the liquid sample mole percent, because that's what it was before it reached equilibrium. As you can see, even from the data itself, going from 100 to 75 to 43 up to 45, the data doesn't look promising as is, so there's going to be an experimental type error there. Okay, so moving on. Using that data, our liquid mole fraction and our vapor mole fraction, we were to fit these to various models to see what is the best model for this composition. This is Raoults' law. As you can see, as Jesse explained earlier in the theory section, this is the ideal model. Raoults' law fits for an ideal solution. So if Raoults' law were to fit, this would imply that the vapor was ideal, that it had occupied no volume, there was no interactions, and there was no interactions in the liquid phase either. Clearly, just thinking about it, a methanol-water equilibrium system shouldn't really fit that because you've got low molecular weight alcohol and water, so hydrogen bonding. So it really makes sense that this doesn't fit either the literature values, which we were plugged against, or our experimental data, even though our experimental data was bad. Okay, so moving on to explain the deviation for Raoults. As I previously explained, this is only for an ideal solution. It doesn't really make sense that it should fit this, just thinking about it common sense-wise. Not to mention that there are no parameters to adjust here in Raoults' law. As it was said before, yi times p equals pi sat times xi. For, I don't know if it was explained, yi was the mole fraction in the vapor solution, vapor phase, xi was the mole fraction in liquid phase, and pi sat was for the component I. So basically here, there are no parameters to adjust. It is merely a function of pi sat, which was determined via ChemCAD via the Antoine equations. So if you go back to the previous slide, as you can see, since there were no parameters to adjust, these graphs are pretty much exactly the same. The only deviation that should be observed for various xi's as calculated by ChemCAD would be due to the slight differences in measured temperatures, which vary slightly the Antoine coefficients, and therefore slightly vary the pi sat. So basically, those graphs are exactly the same, which, thinking about it, doesn't really make sense that it should fit anything, because that implies no matter our experimental data, it's going to give us that graph, which doesn't really make sense. Okay, so then we tried the Van Laar fit. And as Jesse explained in the theory section, Van Laar goes from the modified Raoults' law and says, okay, there exists this correction factor, this activity coefficient, to account for the fact that it's a real gas. And Van Laar has a certain type of expansion to account for that activity coefficient as a function of x1, in this case the liquid mole fraction of methanol. As you can see here, it fits the literature values very well. The blue dots are pretty much on the red line. But our literature values, it gets closer, certainly better than Raoults' law, but it doesn't really touch any of them. Important to note here is the fact that, as you can see, the red lines are different on the left graph and the right graph, which shows that there is an adjusting for the experimental data, which Raoults' law didn't take into account. It said, here, this is what you're going to get. I don't care what your experimental values are. Okay, so moving on to the deviations and the reason for this. Well, Raoults' law and all that was derived from the experimental, the excess gives energy, which is expressed in terms of activity coefficients as expressed in that first equation. Now, because of this, the Redlich-Kistner decided, well, what if we express that in terms of an infinite polynomial series, like Taylor's series, where we can express many functions in terms of infinite polynomials? So what they did is, for Van Laar specifically, they cut it off, just taking into account the A and B, via some algebraic manipulation, and since this is a binomial, a two-phase binary system, you can just have x1 equals 1 minus x2. And manipulation of these coefficients leads to these two equations for the activity coefficients in terms for Van Laar. This A21 and this A12, that's what ChemCAD calculated and adjusted. It said, okay, if A12 equals this and A21 equals this, Here's the activity coefficients, plot it. Oh, that doesn't fit. Let's adjust this, etc. And so that's how the Van Laar was hit. The problem with Van Laar is it has little theoretical basis behind it. It merely says, okay, let's assume we can express the excess Gibbs energy in terms of a polynomial series, and let's see what happens. There's no real reason for that. Also, not to mention, there is no temperature dependence upon these parameters, this A12 and A21, although that can be theoretically and empirically manipulated, although not necessary for this experiment. Next, we moved on to the SRK. Now this SRK, if you note, like Raoults' law, is equal in both the left and right-hand side. So unlike Van Laar, there really isn't anything to adjust. But it fits our experimental data better than Van Laar. It still fits the literature data, just not as well as Van Laar. So that's a discrepancy there that questions whether or not what is the best model. Is it our data or is it the model itself? So, moving on to the theory behind SRK. SRK is an equation of state. It's a modification of the ideal gas law, van der Waals. Basically, Suave came along and said, hey, this Redlich-Kwong equation, let me give a modification to it, and voila. And people decided, hey, this fits the data really well, so we're going to use this. It became an equation of state. And basically, we have these parameters, this B, this alpha, this A, etc. Those are parameters that are dependent upon the composition, what we're measuring here. And basically, it's just a long series of, well, A equals this as a function of phi and gamma is this, and blah, blah, blah. Basically, they're all dependent upon explicit parameters and characteristics of the components themselves. So what I'm saying here is the fact that it's methanol. Methanol has a certain characteristic, critical temperature, critical pressure, and its centricity factor that cannot change. It's a property of the component itself. And because of that, these certain things were manipulated via the equation of state. The Z of liquid and the Z of vapor were calculated. From that, ChemCAD got the phi, which gave us our Y and our X accordingly. Basically, because of that, that previously explains why the previous slide, the two lines were exactly the same. Because again, SRK, because it's an equation of state, doesn't care about our experimental data. It says, these are our components, this is what you should get. So that is sort of a reason to hesitate trusting SRK, even though it fit our data best. Another reason is it's been determined in the lab and empirically that SRK fits best at higher pressures, which doesn't really make sense because we were operating at ambient pressure. So certain models fit better for certain conditions. SRK fits best for high pressure, but this isn't high pressure, so that's another reason to sort of not trust SRK. So, in conclusion, Raoults' law failed. That's to be expected. There's no reason to assume that this system that exhibits hydrogen bonding should be ideal. Van Laar fit well for the literature values, very well. It's pretty much on par. But it didn't really fit our experimental data, whereas SRK fit our experimental data, fit the literature values okay, but not as well as Van Laar. So the reasoning then becomes, which do you choose for the best model for the system? And for previous reasons I've described throughout, the fact that SRK operates best at higher pressure, the fact that it's an equation of state and doesn't really have parameters you can adjust, it tends to, even though in this case SRK fits best, Van Laar still seems to be the equation of choice. However, the only way to verify that would be to rerun this multiple times and basically say, is this just an experimental outlier, or is this in fact the correct model and we've upset the literature values? Okay, so for our recommendations for improvement, we could run cooling water through the refractometer. Basically, the reasoning behind this, there wasn't water running through it, and since methanol is a lightweight alcohol, it evaporates at lower temperatures, low pressures, etc. So the longer the light was sitting there to shine down into the prism, some methanol could have been evaporated, which would affect our refractive index, which would then basically give us faulty data on what our actual compositions were. Secondly, we could have increased the flow rate of the cooling water through the condensating tube. The fact was, the lab said to run it at pretty much a low flow rate, probably not to waste water. But we don't know for sure that all of the vapor coming down the condenser tube was in fact condensed. Some of it could have been leaking out the top, thereby adjusting our composition, our pressure, etc. And thirdly, we could have changed the methanol to octanol, basically just give a different system entirely, because that would make it more clear what we're aiming for. If we changed the system, it would be obvious that, well, this is the best model instead of what is the best model, so we don't have to deal with this. Maybe our experiment's wrong, or maybe this is good enough that this is in fact the best model. And our references were online and our firm above. Any questions?
Questions?
Mine's a quick one.
Okay.
For your graph